Okay, hello everybody. So tonight I'm going to be focusing on sampling distributions with a focus on the normal distribution and the central limit theorem. I'm going to be focusing on answering a bunch of questions utilizing Excel, and I hope that most of these will be helpful to you when you are attempting to do assignment 3. Um, to start off with, I created a quick reference for everybody to utilize when you're thinking about which function in Excel you need to use to answer a certain question. And so down here you have a column that says what information you've been given, and then what you're trying to get, and then which function to use to get that. So for example, if you've been given an individual value to test, either from an individual person or from a sample, you've also been given the mean and the standard deviation, and what you need is the probability of people who are at that value or below that value or above that value. Then you use the norm.dist function that we have seen before. If you're given a sample mean to test, a population mean, and a standard error, then what you need is the probability, then you use norm.dist again. These two first ones are identical, except that in this one you're given an individual's value, and in this one you're given a sample mean. And so the difference here then becomes, instead of using a standard deviation, what you need to use is the standard error. And as I've put down here, if you're not directly given the standard error, then you need to calculate the standard error yourself, and you calculate the standard error using the sample standard deviation and the sample size. So it's the standard deviation divided by the square root of the sample size, and we'll go through that a little bit later tonight. But I do just want you all to notice that the real difference here is testing an individual value, in which case you use the population standard deviation, whereas testing a sample mean, what you need is the standard error. In both of those cases, you're trying to get a probability either of having a certain mean or value, of being below that or above that. And in all those cases, you're going to use the norm.dist function. If what you're given is a probability, so the probability of being below this value is 0.25, you're given the mean and the standard deviation, and what you need is the value. So if I said the probability of being above this value is 0.25, the mean in this sample is 20, the standard deviation is 5. What is the value that corresponds to this probability? Then you put this information into the norm.im function, and that will give you the individual value, the x at that probability. And the same thing is true for a population mean. So this is for an individual again. So if I gave you an individual probability, so what is the probability that so the probability is 0.25, the mean is 20, the standard deviation is 5. What is the individual person's value at this point? Whereas in this one, we're looking for the sample mean that corresponds to that probability. Again, the only difference here, you're going to use the same function, but you're going to calculate the standard error based off of the standard deviation and the sample size of this sample. If what you're given is a z-statistic, so the z value is negative 1.5, what is the probability of having that z value? What is the probability that corresponds to that z value? Then you use norm.s.dist, and all you put in is the z-statistic. And if you put in that z-statistic, it's going to give you the probability of being at that z-statistic. And remember, the reason that it's able to do this is because the z-statistic is simply the number of standard deviations away from the mean you are. And so there is a probability that corresponds with every z-statistic. As we know, you can also use a z-table to look those things up. And then the exact reverse is, if you're given a probability and you need to get a z-statistic for that probability, you can just use the norm.s.im function. So you have 3 different functions here that will get you answers to 6 different types of problems. Okay, so I'm going to focus on 2 exercises tonight. The first exercise has 3 questions, and the second exercise, I believe, has 6 questions. Most of what I'll be showing you will just be in PowerPoint, because I thought that it would be easier for me to put all of the questions in PowerPoint with some explanations with them and the formulas that I use, rather than doing it in Excel. But I do have Excel up just so that I can do it in here for you as well, and just show you what that looks like. I think it is good for you guys to keep seeing Excel and to keep being exposed to Excel, even though really we're just using single formulas each time. Okay, so in the first one, we have a depression scale, and it has a mean of 100 and a standard deviation of 15 in the U.S. adult population. Answer the following questions regarding the results of sampling the U.S. population using this scale. So first, what we need to do is find the probability that a randomly selected individual, again, you need to pay attention to the keywords in the question so that you can be thinking about what formula you need. So we have a randomly selected individual, and knowing that, we already know that what we've been given is an individual value to test. So we're going to use this first function. And what we want to do is find the probability that individual's depression score is between 98 and 102. And also what you want to pay attention to here is the word between. The word between suggests that what you need is a difference in two cumulative probabilities. So you need to calculate the cumulative probability of being up to 102 and the cumulative probability of being up to 98, and subtract the probability of being up to 98 from the probability of being 102, which will give you the probability of being between them. The second question is find the probability that a random sample of 225 adults has a mean depression score between 98 and 102. The sample size for this sample is 225. So here, what we have is a sample of 225 adults, and they have a mean depression score. And so what we've been given is a sample mean to test. And so we know that what we're going to use is this next one, which again is the exact same function. But what's going to change here is we need to convert this standard deviation into a standard error for this specific sample. Then finally, the last question is if we had 1,000 random samples of 225 US adults, what would we expect the average sample mean to be? All right, so in thinking about the first question, oops, sorry, this, I need to edit the question up here. This is from a old example, but the first question is find the probability that a randomly selected individual's score is between 98 and 102. So an adult's depression score is between 98 and 102. So we have our normal distribution here for the population. This population has a mean of 100, and they have a standard deviation of 15. So every 15 that we go down is going to be one standard deviation. That's also the same as one z-score. So if we're thinking about z's on this axis, the z's are going to be one z is going to be every standard deviation, which is going to be every 15 units on this scale. So it's important, if you can, to try to draw out the distribution that you're given and, drop down a line every 15 and put that is 1z, 2z, or sorry, in this case, negative 1z, negative 2z, negative 3z, positive 1z, positive 2z, positive 3z. Put the scores that correspond to those. So 100 plus 1 standard deviation is going to be 115. So a score of 115 is going to correspond to a z-score of 1. Then 115 plus 15 is going to be 130. And so a z-score of 2 is going to correspond to a raw score of 130. 130 plus 15 is 145. So a z-score of 3 is going to correspond to a raw score of 145. The same thing will be true when you go down this way. And that will really help you to think about what you need to do to answer the question. Okay, so we want to find the probability that the infant's PDI score is between 98 and 102. And I've already taken the time to fill in here what the functions we're going to use are, and as I've also filled out their answers, but I am just going to do them in here as well, just so that we get used to seeing these things typed into Excel. Okay, so we have 0.553. This will also help us to correct for the rounding error that we get. So what we just calculated is the probability of being up to 102, of an individual having a score up to 102. So this is a randomly sampled individual from the population. And the probability that they have a score anywhere from the lowest point on the scale, which, it doesn't really matter what that is, but the lowest point on the scale all the way up to 102. The probability of that is 0.55. Now, if we want to score, if we want the probability between 98 and 102, we need to subtract the left portion of the tail that corresponds up to 98. So what we have here is 10. So let's say 102 is about right here. What we've just calculated is all of this section that goes up to that point. But what we really want is just the section between 98 and 102. So if you take the time to draw out your curve, it will really help you to figure out what you need to do. So you draw that out and you realize, okay, I actually only need this section, not all of this. And so what you then need to do is calculate the probability up to 98 and take out the part to the left, because that part of the probability, that part of the tail, that left-tailed probability is not part of the probability between 98 and 102. Okay, so then we need equals norm dot dist of 98 comma 100 comma, and again, I hope you see what I'm putting in here. Here we have the x value that we're testing. Here we have the population mean. Here we have the population standard deviation, and here we have true because we want a cumulative distribution. We would only put false if we wanted the exact probability of having a score of 102. So what is the probability that an infant, or that a individual, sorry, again, I accidentally have infant here, that an individual adult has a score of exactly 102? That's going to be a pretty small probability. What we want is the probability of having a score up to 102. And so we put true here. And so we get that that probability is about 0.44. And now, again, what we need to do to get the probability between 98 and 102 is subtract the probability of 98 from 102. So we take the probability up to 102 and we subtract the probability up to 98. And this gives us the probability between 98 and 102. So that answer is 0.106. So the probability of being that close to the mean, so the mean is 100. The standard deviation goes all the way out to the first standard deviation goes all the way out to 115 and all the way down to 85. So being only between 98 and 102 is a pretty small section of this curve, and we find out that that the total area of that section is 0.106. There is, of course, another way that we can answer this question, and that other way of answering it is by using z-scores. So we can also find the probability that the adult's score of depression is between 98 and 102 by calculating z-scores. A z-score is simply the x value, and by the way, this is what Excel is doing when you type in that information to it. It's calculating that z-score and then using that z-score to calculate the probability. You can also give it that z-score, or if you're given the z-score, then you can do it this way. So you can start by calculating the z-score, or if what you're given is the z-score, then these are the functions you're going to use. You want to calculate the z-score by taking the score you're looking for, which is 102, subtracting the mean, and dividing by the population standard deviation. We want to do the same for the score of 98. So it's 98 minus 100. So you can already see here that we're going to get a negative number. This makes sense because we should have a negative z-score because we're in the part of the curve that's below the mean. Then we're going to divide by the population standard deviation. Not surprisingly, because they are symmetrically distanced from the mean. So this one is 2 units below the mean and this one is 2 units above the mean. Their z-scores are identical, but they are different signs. This makes complete sense. If something is an equal distance from the mean above and an equal distance from the mean below, they will have equal z-scores. Normal distributions are symmetric, and so no matter which way you're going, the z-score is going to be the same. It's just the sign. So if I'm moving 5 units to the right versus 5 units to the left, those z-scores are going to be exactly the same. It's just that the sign is going to change. And so if you can remember those properties of the normal distribution, it can be an easy trick for answering some questions rather than subtracting from 1, for example. Excuse me. Okay, and then to get the probabilities that correspond to these z-scores, we are going to take equals norm dot s. So this is one we haven't used before. We use norm dot s dot dist if all we have is a z-score. So if all we have is a z-score, Then we use norm.s.dist. We put in that z-score, and we put whether or not we want this probability to be cumulative, which again, just like in the previous section, these we're answering the same exact question. We're just using a different function with slightly different information, but we still want that cumulative probability, so we're going to put true there. And then we're going to do the same thing here, norm.s.dist of a z-score of negative 0.133. And it's true that we want cumulative again. Now notice, please, that the probabilities are not the same. Probabilities do not work that way. Probabilities are cumulative, and so probabilities always get larger, starting at the lowest point, not starting at the mean. So unlike z-scores, which start at the mean and increase to the right and decrease to the left, probabilities start at the lowest point and increase constantly until the highest point. So don't get confused when I say that normal curves are symmetric and think that probabilities will have that same property, because they don't. And then we need to subtract the probability from the probability, and we get the exact same answer that we had before. So two different ways of answering the same question. In one, we calculated z-scores first and then found the probability associated with that z-score. In the previous, we put in the x values that we wanted to test, as well as this mean and standard deviation, and Excel under the hood calculated those z-scores for us and gave us those probabilities. But again, in some cases, you may only be given a z-score. And so if you're only given a z-score, you put that z-score into this function, and you're going to get your probability. Okay. The next question was to find the probability that the sample mean depression score is between 98 and 102. And the sample size is 102, or sorry, sample size is 225. All right. So in this case, we are looking for a sample mean depression score between 98 and 102. So what that immediately needs to cue you to is that instead of using the population standard deviation, you need to use the standard error. And to get and you're going to have to calculate the standard error. So in this case, we are going to use equals norm.dist. We again are going to use 102. We're again using a mean of 100, but now we need to enter the standard error instead of the standard deviation. So instead of entering 15, we are going to enter the standard deviation of 15 divided by the square root of 225, which is our sample size, which I've already calculated that up here for you. The square root of 225 is 15, so it's actually 15 over 15, which is 1, which is a nice property of this. But I'm not even going to put 1 in there. I'm going to put this exact formula in there just to show you that you can plug these formulas in just as easily as you can plug numbers in. And then again, we're doing true. Now, I want to point out that's 0.977. Here, it was 0.553. So the probability of a sample mean being up to 102 is almost 100, whereas the probability of an individual value being up to 102 is much lower. Similarly, we have norm.dist. The x now is 98, 100. Then we're going to put in 15 divided by the square root of 225, comma, true. And we have 0.02. So again, probability of an individual that you randomly draw having a score of up to 98 is about 0.45. It's not bad. It's about 50, almost 50-50. The probability of a sample mean being 98 or less is only 0.02. So very unusual. And then we're going to take the higher and subtract the lower, and we get about 0.95. So the probability of drawing a sample of 225 individuals that has a mean between 98 and 102, when the sample has a mean of 100 and a standard deviation of 15, is very high. The probability that you're going to get 225 adults and that their mean, when they're drawn randomly from this population, is going to be lower than 98 or higher than 102 is not good. The probability of that happening, which would be 1 minus this, is about 0.45. So there's very low probability that an entire sample of 225 people are going to have a mean that far away from the population mean. It's a lot easier to find one person whose mean is that far away from the population's mean than it is to find a sample of 225 people randomly selected from that population whose mean is that far away. Okay, and then the final question was, if we had 1,000 random samples of 225 US adults. So we just saw the probability of having one sample. If we have 1,000 random samples of 225 adults, which are going to look a lot like the sample we just looked at, what would we expect the average sample mean to be? The answer here is that with this many samples of this many people, we expect the sample mean to be the exact same as the population mean. Why? Because the central limit theorem tells us that if we collect enough large random samples from the population, the means of those samples should be normally distributed around the population mean, which means that their average will be the population mean. And this makes sense. If we are collecting a ton of people from this population, the mean of those samples should be equal to the mean of the full population, because we're getting a large sample of the people in that original population. So when we're getting a large sample of people from that population, it makes sense that we would expect the sample to have a nearly identical mean as the original population. All right. So now we're going to do a second exercise, and we're going to be using very similar types of things, just to go over this again, give you some more examples of them. Here we have a measure of depression that has an average score of 20 and a standard deviation of 3. You collect a sample of 300 adults. And so we're going to be doing a couple of things. We're going to find the probability that a given individual's depression score is between 19 and 21, something very similar to what we just did before. We're going to find the probability that a given individual's depression score is less than 17. And we're going to report the z-score for a score of 17. Or for a score of 17 or lower. Find the probability that a given individual's depression score is higher than 22 and report the z-score for a score of 22. Find the probability that the sample mean depression score is between 19 and 21. And find the probability that the sample's mean depression score is greater than 23. So these are all pretty similar to what we just did. We are just taking some time to review them again. Okay, so find the probability that a given individual's depression score is between 19 and 21, keeping in mind that the sample's mean is 20, the sample's standard deviation is 3. So what we know already, again, please read these, think about the information. The first thing we know is we're looking for an individual's score. So we're going to use the population standard deviation. We're not going to use a standard error. There's no way to calculate a standard error without a sample size. So it would really be impossible to do that. So what we're using is the population standard deviation. And we're looking for the probability that it's between 19 and 21. So we know that we need to calculate the cumulative probability of 21 and subtract from that the cumulative probability of 19. We might also just want to think for a minute about where 19 and 21 are relative to the mean and standard deviation. The mean is 20. So each of these, so 19 is 1 unit below 20, and 21 is 1 unit above 20. So these are a symmetrical distance from 20, from the mean, which means their z-scores will be exactly the same, but in opposite signs. And we also know that the standard deviation is 3, and these are each 1 unit away. So what we know is that they're each 1/3 of a standard deviation above and below the mean. So without even doing any calculations, we know that the z-scores for these are going to be about 0.33 and negative 0.33. I have not done any math except to take 1/3, except to divide 1 by 3, and to know that that 1/3 is 0.33. And to know that the distance in standard deviations, so this is 1/3 of a standard deviation above, 1/3 of a standard deviation below, which means the z-scores are -1 divided by 3 and +1 divided by 3. Okay, so we are going to take an equals norm dot dist of, well, let's do 21 first, comma 20, comma 3, true, and then we'll do 19. Okay, so we get 0.63 and 0.36. And then all we need to do is take 0.63 minus 0.36, and we get 0.26. So there is about a 25% probability that you're going to be within this section. And let's go back to that normal distribution for a second. Why do you think that is? That's because we are in the part of the curve right here that is the highest. And so it has the most amount of area. So if we think about the amount of space under this curve, there's very little space between one unit of curve here, just this tiny little triangle of space. But in one unit here, we have a whole bunch of space. And so the probability of being within 1 unit of the mean here is quite high. Okay. So, and again, if we do this in Excel, you'll see here, I copied the numbers over and rounded them. And so we got a little bit of rounding error here, 0.262. Here it's really 0.2611. Of course, in the assignments and in the exams, we allow for rounding error. So this would not be marked wrong. But it is helpful if you can do these things in Excel the whole way so that you don't have to deal with rounding error. All right, the next thing we want to do is find the probability that a given individual's depression score is less than 17 and report the z-score for a score of 17. Okay, now again, we can certainly do the math, and I'm about to do the math, and I've already written this down here, but the first thing to recognize is that the standard deviation of this curve is 3, and 17 is exactly 3 units below 20. So without doing any calculations, I already know that 17 is 1 standard deviation below the mean, which means it's exactly a z-score of -1. It's 1 standard deviation below the mean translates to a z-score of -1. A z-score is just a number of standard deviations. Z is, it's a confusing letter. It doesn't really tell us that it's the number of standard deviations, but that's exactly what it means. A z-score is simply the number of standard deviations a value is above or below the mean. Okay, so norm.dist 17, 20, 3, true. So 0.1586. And then we want so the probability that a given individual's depression score is 17 or less is about 0.16. And I've already told you that the z-score for that is going to be -1. But if you don't recognize that, or if it's not as simple as being exactly 1 standard deviation above or below, we can use either the norm.s.im function with the probability that we just calculated, which is -1, or we can calculate the z-score ourselves. So there are a variety of different ways to get from one thing to another using Excel functions. Excel here now took a probability and turned it into a z-score. So before we took a z-score and we turned it into a probability. Now we've taken a probability, we've turned it into a z-score. But we can also calculate that z-score ourselves by just taking the value minus the mean divided by the standard deviation. And again, we're getting -1. Not surprising. Okay, find the probability that a given individual's depression score is 22 or higher. Report the z-score for a score of 22. All right, so now we know how far we are from the mean. Standard deviation is 3, and we are 2 units above the mean. So we're 2/3 of a standard deviation above the mean. So guess what? Our z-score, without even calculating anything, is going to be about or about 0.66. So we do equals, to find out the probability, we do equals norm.dist 22, comma 20, comma 3, comma true. And that probability is about 0.75. And then we need to know the probability that you're above that score. And so instead of having 0.75, let's go back to the normal distribution for a second. So we just calculated the probability. So this is not, this number doesn't apply here, but just look at the curve and think about the fact that we just calculated the probability of being above the mean by a certain distance. And Excel always gives us left-tailed probability. So what we have is all of this curve, all of this part. We have all this left part. But what we want is the probability of being over here, being above that. So what we need to do is know that probabilities sum to 1 and do 1 minus this probability that we just calculated. And so what the actual probability is here is 0.25, not 0.75. This is a place where you can easily trip up on an assignment or exam if you don't pay attention to the sign or to the direction you're looking at. If you have a left-tailed probability, it's going to say less than or equal to, then, all you have to do is calculate it in Excel, but it can be very easy to be thrown off by being asked what the probability is of being greater than that. And if that's the case, what you need to do is subtract it from 1. That is going to be an area where some people are going to trip up on the exam and the assignments, I'm telling you right now. So pay attention to the direction to the side of the curve that they're asking you for. Are they asking you for a left-tailed or are they asking you for a right-tailed? If what they're asking you for is a right-tailed probability, then you have to remember to subtract a left-tailed probability from 1. All right, and then we also want to report the z-score for a score of 22. So we can either calculate the z-score ourselves, which is going to be equals 22 minus 20 divided by 3. So 2/3, as I already told you, because what we know is it's 2 units above the mean and the standard deviation is 3. And so it's just 2 over 3. Or we can use the norm.s.inv function, and we can take the probability that we calculated. So the probability, though, that we need to use here is we do have to use the left-tailed probability here. Again, Excel will not deal in right-tailed probabilities. So even though we calculated the right-tailed probability, and that's correct, if you put the right-tailed probability in here, it is going to think that you mean whatever value has a left-tailed probability of 0.25. Excel has to receive a left-tailed probability here. So you need to go back and put in the 0.74 probability and not the probability that we actually wanted, because Excel doesn't care in this case whether you're talking about higher or lower. Regardless, you need to put in a left-tailed probability here, which is why it could be helpful if you think about conceptually how many standard deviations are you above or below the mean, and try to get a guess of what your z-score is before you even calculate it, so that when you calculate the exact value, you know if you're way off. If your z-score is in the wrong direction, you should be able to recognize that, and you'll know that you put in the wrong probability for that. The other option is to calculate it manually like I did here, and just do 22 minus 20 divided by 3, and then you don't have to worry about putting in a probability, unless what you're given is a probability. Okay. Oops. Okay, the next one is to find the probability that the sample's mean depression score is between 19 and 21. So before we found the probability that a individual's value is between 19 and 21, and that was 0.26. So finding one individual in the population who has a mean anywhere between 19 and 21, we have about 1 in 4 chances of doing that. That is not going to be the same for a population. I would like you to think for a minute about whether the probability of finding a sample mean between 19 and 21 is going to be greater or lesser than the probability of finding one person between 19 and 21. I already have the answer down here. The probability of finding a sample mean between 19 and 21, when you have a population mean of 20 and a population standard deviation of 3, and your sample size is 300, it's going to be much, much higher to find a sample mean, because the sample means are going to tend to be much, much closer to the population mean than any individual's value. The probability of finding an individual that's far away from the population mean is not that hard, because the normal distribution even has people who are several standard deviations below and above the mean. That's not weird. However, to find a sample whose mean is that far away from the population mean is a lot harder, because what you have is a bunch of people. And so you have a relatively decent representation of that normal distribution of the population. Okay, so we're going to do equals norm.dist of 21, 20. And then again, here, we need to use the standard error. We're talking about a sample's mean now. And so you need to recognize that what we need to put in instead of the standard deviation is a standard error. And the standard error is calculated by the population standard deviation divided by the square root of the sample size, which in this case was 300. And then we want true. And so you can see that there's almost no chance of finding a population mean above above 21. So the probability of finding a population mean anywhere up to 21 is almost 1, which means there is almost a 0% chance of finding a population whose mean is above 21. And then we have equals here, norm.dist of 19, 20, square root of 300, 3 divided by the square root of 300, true. And now I just want to point out quickly, this is scientific notation, which I understand that probably a lot of you may not have seen in a very long time. And even if you have seen it more recently, you may not have seen it like this. So scientific notation is what I have right here. It is when you have something, a number times 10 to a positive or a negative value. And what that means is if 10 is to the negative value, it means you need to move the decimal place 9 times to the left. So 1, 2, 3, and put a 0 everywhere that you move it. So here we don't need to put a 0 because there's already a number there. But for every other space that we move it, we're going to add a 0, which means what we have here is point and then 8 zeros and then 388. So this is an incredibly small number. If this was 10 to the 9th, what it would mean is move the decimal place to the right. Now, you don't really need to know this for this class. The point here is that 10 to the negative 9th is basically 0. It's 0.0000000388. So that's, you can't get much closer to 0 than that. Excel will represent that using an E instead of a 10, because it wants to be able to put all of this as one single number rather than telling you to multiply it by 10 to the negative 9th. And so it's going to say e to the negative 09. If you ever see an e in your number, you didn't screw up. Excel is not giving you some sort of weird error. Excel is telling you that what you have here is an incredibly small number. If you see e to a positive number, then what you have there is an incredibly large number approaching infinity. All right, so knowing that, we have basically 0 here and basically 1 here. So we know that when we subtract almost 0 from almost 1, we're going to get something that's almost 1. Okay, so not surprising. We have a number that is very, very far from, very, very close to being 1, which means the probability of finding a sample whose mean is between 19 and 21 is almost 100%. There's almost no chance of finding a sample that's got a mean below 19 or above 21. Now, of course, that's not impossible. There is still always going to be a slight probability that that is possible in the world by chance. But finding a random sample of 300 people whose mean is below 21, or sorry, excuse me, below 19 or above 21 is almost 0%. Okay, the next question is to find the probability that a sample's mean depression score is greater than 23. Again, I urge you, please, with each question, take the time to underline it or write down the details. The first detail, it's a sample mean, and what you're given is a sample mean. What you need is a probability. And what you need is a probability greater than 23, which means you need a right-tailed probability, which means what you're going to calculate is a left-tailed probability, and then you're going to subtract it from 1. Please, please, please pay attention to that, because it will trip some of you up on the exam. And I'm just trying to warn you now, please try to notice those things, because you have to subtract them from 1, otherwise you're going to have the wrong answer. Okay, so equals norm.dist. We want 23, comma 20. And then again, because we're talking about a sample mean here, we have to use the standard error. Now, please feel free to go back to the very first slide on this PowerPoint and just reference it every time you have a question. Think about it. Circle what you're given. Circle what you need, and then figure out which function to use. I've even put in there a note that you need to use a standard error if you're looking for a sample mean. You need to use a standard deviation if you're looking for an individual value. It's all right there. Please feel free to use it as a reference. So here we need the 3 divided by the square root of 300, comma true. And so that is basically 1. But then remember that we need the right-tailed probability. So we need to take 1 minus this value. And not surprisingly, 1 minus 1 is about 0. We already knew this because we had already found out in our previous question that the probability of being outside the range of 19 to 21 was virtually 0. Almost all samples are going to have a mean between 19 and 21. So being above 23 is incredibly, incredibly, incredibly improbable with this sample. And that is actually everything that I had to go over tonight. I will post the slides. I will go through and make a few corrections for some of those areas where I had things saying infants and whatnot, and I'll post those in just a few minutes. I do hope that this helps you with the next assignment as well as with the exam. And as always, if you have feedback, things that would be more helpful, feel free to shoot me an email. Thanks. Have a good night.